Hello, everybody. Dr. Ross here with some notes on an introduction to entropy, and just to give everybody a feel for what entropy is, at least at the general chemistry level. Okay, so I'm sharing some notes. These notes are provided to my chemistry students as usual. And I'm going to set this up so I can annotate. All right. Okay, so I start off with a preface to entropy. So what is entropy? So just to gear us up to some notes and discussions about entropy. What is entropy and how are some ways to contextualize it? Well, the laws of physics don't have a preference for direction for small samples. So this idea of irreversibility or a preference for direction really crops up when you get to a certain amount of material. So for example, if we look at the example here, consider two hard spheres colliding and bouncing off each other. So if you look at this diagram from left to right in the positive time direction, we have a white sphere and a black sphere coming in. You can see the direction of the arrows here. They come in and they collide at an event at some time t. And then the black sphere hits the white sphere and goes on its merry way up that way. And the white sphere hits the black sphere and goes on its merry way that way, as shown by the arrows. And you can see that this diagram, roughly speaking, has a plane of symmetry. So if I just highlight what I mean by the plane of symmetry. So roughly speaking, about this point, if I were to go back in the negative time direction, to go back in time, I would recover exactly the same event. So this is, if I imagine that this dashed line is a mirror, so the left and the right are just mirror images of each other. So clearly, if you view this collision in the plus and minus time directions, it looks the same. So it looks indistinguishable. Okay, so that agrees with the laws of physics, that you can go forwards and backwards in time with the same equations. However, that quickly doesn't become the world that we live in. So let me clear my drawings because they don't travel when I scroll. So now let's imagine a larger system where we have more spheres or more atoms or molecules or whatever the sphere represents. A larger system would be distinguishable in the plus and minus time directions. So let's see, on the left, we have a black sphere come in the positive time direction, and then it collides with a collection of spheres. And you can see that each sphere goes off in a separate direction. Now, clearly, I don't even need to draw this, but I will anyway. But clearly, we lack that sense of mirror image. So the left and the right are clearly different. And if I were to play this in the reverse time direction, it would look clearly different than if I played it in the forward time direction. This seems to be more representative of the world we live in. Things, for example, eggs smashing on the floor looks different than eggs coming back up off the floor to an intact shell. So in the real world, this tends to be a distinction between forward and reverse. Okay. So moving on to these notes, it says there seems to be an order to change that follows time. There is, this is how we can tell if we're watching reality in the plus time direction or in the negative time direction. So for example, if somebody reversed a video and played it to us, it would look fake. So if you saw somebody spring out of a body of water, clutch their knees and land on the side of a pool, you would know something was wrong with that. Water molecules don't spontaneously coalesce to eject a swimmer from a pool and land them squarely on their feet on the side of the pool. That just looks fake. It looks wrong. It would be awesome, but something looks wrong. So however it looks wrong to our intuition, no laws of physics explain why, at the fundamental level, why there is a problem. Why is it wrong? Other than it just looks wrong. So to address this problem, Gibbs, Boltzmann, and many other people looked for ways to explain change as time progresses. So now you roughly know what entropy solves. It's the solution to this apparent arrow of time, this temporal flow of information, I guess. They came up with the idea of entropy, and although they considered entropy differently, slightly differently, entropy is the correct way to think about change with time, as far as we know. Okay, so let's look here at hard spheres again, colliding, but the collisions we're going to look at as a defocusing phenomenon. So if you look at sphere 1, sphere 1 is going to collide with sphere 2, and then sphere 2 is going to collide with sphere 3, etc. So if we hit sphere 1, and sphere 1, let's say we'll do it twice and it has two subtly different trajectories. So we can see that there's initially a small difference d in the trajectories. If sphere 1 hits sphere 2 square in the middle, then sphere 2 might hit sphere 3 on the right side of sphere 3, and then it would ricochet off to the right side. However, a slight deviation in the trajectory of sphere 1 would mean that it might clip sphere 2 on the left side now, would therefore hit sphere 3 at a different component, here the left side, and would go off onto a left trajectory. So a subtle difference d in the initial trajectory of sphere 1 can have almost 180-degree difference in the final trajectory of sphere 2 after it hits sphere 3. So in short, the small difference in trajectory gets magnified, can lead to a very large difference in later trajectories. So it becomes defocusing. So due to extreme instability of the sphere's trajectory to small changes in the initial conditions, mixing naturally occurs. So mixing here is this idea that we get this divergent trajectories caused by initial previous deviations in trajectories. Defocusing is somehow, you'd expect, proportional to the number of spheres in the sample. And we saw that earlier with the greater sample size leads to lack of reversibility, and that lack of reversibility, you can think of that as being a defocusing phenomenon. So exactly how does it work? So now we're kind of prepped for what entropy can help us with. Let's look at entropy proper. Entropy, and if you look at entropy, there's different flavors of entropy, but we're considering the thermodynamic version here. So entropy, to look at entropy proper, we want to look at probability. And probability P, we're going to say, is proportional to 1 over our ignorance, W. So let's have a look at what that means. So let's say we take a marble, and the marble here, we're going to, let's say we're a fair, like the Orange County Fair or the Los Angeles Fair, and we're going to flick a marble, and we're going to try and see where it's going to land. And there are 8 possible locations it can land. It can land in location 1, location 2, etc., through location 8. So each of these separate locations we'll just say generically is location I, where I has values 1 through 8. So imagine a marble is tossed and lands in slot 4 of I possible slots. Then the probability of guessing which slot the marble will land in is the 1 correct value over all of the options. So 1 correct value, 1, divided by the number of options, 8. So we've got an 8th probability of guessing it right. Because the right answer 4 out of the options 8 is exactly 1/8. So if our ignorance is inversely proportional to probability, and we know our probability is 1/8, therefore the ignorance is 1 over probability, which is 1/1/8, which is just 8. So our ignorance W is proportional to 8 to the number of marbles 1, which is equal to 8. If we had 2 marbles, then our ignorance to the outcome would be 8 to the power of 2 marbles. So the possible outcomes, there are 8 of them, but now we have 2 marbles. So it would effectively be 8 squared. So it would be 64. So if I were to guess correctly where 1 marble is going to be, I've got better odds than if I had to guess correctly where 2. And you can see here that the more marbles I have, I raise it to that order. So 3 marbles would be 8 cubed. 10 marbles would be 8 to the power 10, etc. Okay. So we remarked that clearly the number of objects impacts the ignorance of the system. So the more objects I have to know about, the less probability I have to know about them, and therefore the more ignorant I am. So you imagine how ignorant one would be about the molecules of gas in the room that you're sat in right now. It would be an insurmountable task to try and keep track of all of them. So to make the exponent population dependency a quantity dependency, we take the log of our ignorance. So again, it looks like my ignorance is dependent on the population, but I would like the population to be a coefficient rather than an exponent. So we just use the mathematics of logs, which can be used to convert exponents into coefficients. So for 1 marble, I take the logarithm of my ignorance, and in the thermodynamic way of looking at entropy, we take the natural log, or the log base E. That's the appropriate log. So the natural log of my ignorance is proportional to 1 log 8. For 2 marbles, the natural log of my ignorance is 2 log 8. And for n marbles, the natural logarithm of my ignorance is n log 8. So again, when I log, I can convert the exponent to a coefficient. So originally, before the log, these coefficients were exponents, right? So the purpose, if I want that 2 to become a coefficient in the case of 2 marbles, I need to add the log. So there it is. Okay, this is on first inspection a scary looking equation. It's got funny exclamation marks that you may or may not be familiar with. Good news is I'm going to explain what they mean. Better news is they're going to disappear in a minute, so we don't even have to worry that much about them. Let our ignorance be, as we stated, W, but let W specifically equal capital N factorial over the product of the little n's all factorial. So n is just the total sample, capital N for total number, and then the little n's are the parts or the kinds of things, the bits of information within that total. And factorial just means, so for example, maybe I can add this on here. Let's see if I can just remind everyone what factorial means. Do I have any space before I start doing this? Where do I have a little bit of space? I don't have much space, do I? Maybe I'll squish it in at the bottom. Yeah, I'll squish it in at the bottom. Okay, so this will be a quick aside on factorials, because I guess I don't give you an aside. So for example, 3 factorial just equals 3 multiplied by 2 multiplied by 1. 4 factorial just equals 4 multiplied by 3 multiplied by 2 multiplied by 1. So as you can see, factorial just says take the number and then multiply it by the number minus 1 until you get to 1. 10 factorial would be 10 multiplied by 9 multiplied by 8 multiplied by 7, etc. Okay, so that's what we mean by factorial. And the good news is a modern scientific calculator just has a number. So you can just hit 3 factorial and make sure you get 6, and then you basically know what you need to know about factorials. Okay, so let's have a look at, so that's what factorial means. So therefore, if we take the log of our ignorance, W, then we have to log both the numerator and the denominator. So we take log base C of the numerator, log base C of the denominator. The problem is you can't take the logarithm of a factorial. So you have to find a way to abbreviate the factorial or approximate the factorial. And we're going to use an approximation of Stirling's approximation, which is any number factorial is the number log n minus the number. So that's something that you'll see several times in the following few pages. Okay, so if we apply this to our numerator, log n factorial, we just get n log n minus n. So this here is our numerator. This thing here is just our numerator using the approximation of Stirling's approximation. Now, the minus sign here is just because I have a fraction of logs. So remember from your log rules, if you have log A divided by log B, you just have the difference of logs. So that's where that negative comes from. It's just the fraction of logs. And then I look at this sum. Where on earth does this sum come from? Well, I've got the denominator is the log of a product. So these are all products, right? The things multiplied together. And I know from my log rules that if I log a product, I sum the individual logs. So I've got to log all of these lowercase n's here. So I've got to sum them all together and apply Stirling's approximation. So I just have n log n minus n, that's the Stirling approximation for an n, and I apply that n to however many n's I have. So let's just generically call it ni. So ni log ni minus ni. And then I have to sum over all the i's because I have the log of a product. So that's where the sum comes from. So hopefully that's clear and it all makes sense. Okay, so next we notice something kind of cool. So we notice that the sum of the little n's is equal to the big N. So the sum of the parts is equal to the whole, right? That's what I'm trying to get at here. The sum of the partial n's is equal to the total n. And I noticed that, so let's clear some of these drawings real quick and then I'll freshly annotate what I'm looking at now. I noticed that here I have minus a big N, and over here I have this minus the sum is going to eventually hit this negative n. So the sum of the little n's, but the minus and the minus make a positive, and the sum of the little n's makes a big N. So the sum of the little n's with the minuses makes a positive big N, which when I add it to the negative big N is just going to sum to 0. So the sum stays in my final equation because it applies to n log n, but I no longer need it to apply to this minus n over here. So hopefully that made sense, and I've now lost the big N, and I've lost this guy. So I just have the logarithm of my ignorance is n log n minus the sum over all I, little n log n. Okay, so hopefully that, maybe if you pause the video, makes a little bit of sense. And so let me just say something here that I actually don't have on these notes, but let me comment real quick. So this will just be a comment. So whatever this log of our ignorance is, so the logarithm of our ignorance, whatever that might mean, well, if you look at this, the only difference between these two expressions, oh, that should have gone up there. This looks like the total something, and then you've got the minus, and then this looks like the sum of the parts. So no matter what W means, just consider that statement. The total minus the sum of the parts. Well, you would imagine that should be 0, right? So I'm going to put 0 question mark. You know, if the total is the sum of the parts, then the difference between the total and the sum of the parts should be 0. If it was 0, life would be so much more easy, but very less complicated, or much less complexity, and therefore very boring, and we would not be here. So just keep that in mind as we move forward and look what exactly we're going to get to what log of our ignorance is. So let P, the probability for I, be the probability of having the specific value I. And then let's just make some assumptions. Let Ni, so a specific value N, be the total multiplied by the probability of I. So the probability of I is just the probability of having a value Ni, and it comes out of the total N. Okay, so that's our first assumption. And then our second assumption is let n log n equal npi. So remember npi, because from here, ni is npi, then if we take ni here, we can just replace it with npi here. And then again, we've replaced this ni with npi. So hopefully that makes it really clear. Okay, so we've got that. All right, so based on those statements, let's recall from our previous page that log w, the logarithm of our ignorance, is n log n minus the sum over all I of ni log ni. And now we can substitute in this ni log ni. We can sub all of this information in, so you can see it here inside the parentheses. And then you notice that we've essentially got, if you look at the n and the p, we've essentially got a product. So we've got the logarithm of a product, so we sum individual logs. And we have this NPI applying to both. So the NPI is a factor that applies to the log of n, so we do that here. Plus, because we have the log of a product, the NPI also applies to the log of pi. Okay, so we've just factored out the square braces here. And then we notice that we have a common factor that we can cancel. We have to the left of the equation, we have n log n. And then we've also got this factored out n log n here. Here I've just factored out the pi from both. So each term in this plus here has a pi. So I factor that out. And then I'm left with n log n. And I'm left with n log p. I can't factor that p out because I can't factor the log out, but I can factor the multiple of p. Okay, so I cancel the n log n's, and then I just see where I'm left with. I'm left with negative the sum over the probability pi, n log pi. I guess I've missed writing the log out again, the n out again. So that was just a little omission. I'm sure anyone that's awake would have seen that. So I've got that factor of n in here. All right. And then I can factor that n out just because it's a constant. So I get it outside the parentheses, and I'm left with my final equation. Logarithm of my ignorance is minus the sum over the total sample, the probability of I log the probability of I. All right. So that's my final equation. This is just to try and make it, just to try and link it back with probability. Remember that the logarithm of our ignorance is proportional to the size of our sample n. So we know that log w here is our ignorance, is proportional to n. Recall at the beginning of this video, we said the probability was proportional to 1 over our ignorance. Why did I say log 1 is, well, why did I say log 1 period? Let's see if I can, why do we say log 1? Oh, well, if we take ignorance of 1, so it's just a case, it's just because we can make that term vanish. So if, for example, our ignorance is 1, then the log of 1 is 0, right? So we can make this term disappear. And then we can basically say, therefore, that the logarithm of our ignorance just becomes proportional to minus log p. And if you look at the equation we had just at the top of the previous page, so this final equation here, then you can see what you have. You have logarithm of our ignorance. If we replace the equal sign with a proportional sign, and then we ignore this constant of proportionality here, we're just left with minus logarithm of the probability, which is what we set up here. So it essentially just justifies, I guess the important thing is here we have this, it's exactly, in fact, let me just write this down here. I think the following will clear this up. So if you look at this here, then recall that log a over 1 is negative log 1 over a. So you take the inverse of the argument and then log it, you change the sign of the log. So if I log, see the way I've got probability and ignorance as numerator and denominator. If I want to express them both as numerator, one of them's got to be negative with respect to the other if I log them. So that's why you have a plus here and a negative here. So this plus and this negative, this reminds you that W is proportional to 1 over P. Okay, that's what I'm trying to say in a very long-windy way. Okay, so let's look at the summary. So we've got log W is proportional to something called entropy. So now we can finally put a label on what we mean by logarithm of our ignorance. It's something that's proportional to a value called entropy. Gibbs entropy here, the G stands for Gibbs. Again, we've got capital N, that's total number of items in our sample, and PI is the probability of item I. And actually, we're gonna give a visual, or not a visual, a notion for what we mean by ignorance, because ignorance is very abstract and ethereal. We mean the volume of phase space. So phase space might also be equally abstract and ethereal to some, but at least it gives a name, an extra name that that we can look for. Okay, so we look at Gibbs thermodynamic entropy. If I want to make that proportional sign into an equal sign, I've got to add Boltzmann's constant KB. But it's usually quite okay just to set Boltzmann's constant equal to 1, so we can express entropy values in multiples of Boltzmann's constant. So you can just say proportional to, or just set Boltzmann's constant equal to 1. Okay, so let's look at this grid. I apologize for the scribbles. I ran out of whiteout when I made these notes. Okay, so let's look at this grid. So just to orient you as to what on earth this grid means, we have, let's say in grid A, we have only one possibility. So these values here are measuring probability. So let me annotate what this is. So this is meant to be a probability. Okay, so there's only one possibility of where that atom, the dot represents an atom or a molecule. It's going to be in square A. So I know exactly where it is. It's probability 1. In square B, or in option B, there are 2 squares, and you can either be in square on the left or in square on the right. So let's just say, and here I'm just deliberately equally populating the squares. But let's say there are 2 probabilities, so 0.5 on the left, 0.5 on the right. In option C, there are 3, so a third each. Notice they must always sum to 1. 0.2, 0.2, 0.2, 0.2 sums to 1. And then if there are still 5, but if I start to double up, then each of the single occupancies, obviously this would have twice the probability of any of the singles, but they must still sum to 1. Okay, so that's all you have to know about that. Now let's write down our entropy for each of these situations. So the first one, I had probability 1. So I just put the probability in before and after the log, and I get an entropy of 0. And that's because log 1 is 0, and the 0 multiplies everything by 0, and it returns a 0. Okay, if my probability now is a half, well, I've got a half for the one on the left, and I've got a half for the one on the right. So I have the sum of these guys. And so I just return a value of 0.693 multiples of KB. So the entropy has increased from 0 to 0.693. For item C, where there were 3 options, I have a third log a third plus a third log a third plus a third log a third. That gives me 1.098 multiples of KB. So again, entropy has gone up. as you would expect, because the number of possibilities that are going up, or my ignorance is going up, because there's more stuff to know about. And 4, you've got 4 multiples of a quarter log a quarter. 5, you've got 5 multiples of a fifth log a fifth. Now here where I doubled up here to put 2 in the same one. Then I would have 4 identical lots, so 4 lots of 0.17 log 0.17, and then I've got 1 lot of a third log a third, and that would give me a slightly lower entropy, because obviously I'm doubling up. I'm starting to congregate, so spreading out, it seems, increases log. The spreading out from 1 box through 5 boxes steadily increases entropy, but the accumulation here starts to lower entropy. Okay, so that's interesting. The purpose of this slide is just to show you how to plug numbers in, basically, into that equation. Okay, let's move on to a topic that will be useful, again, to help you visualize. Let's look at core screening. So we're going to use core screening as a mental model to replace probabilities with what we call probability densities. Okay. So we're going to look at Boltzmann's idea behind entropy. So how can I visualize the progression to exponentially larger coarse-grained phase space? So volumes in a chemical system as time, how can I visualize the progression to exponentially larger coarse-grained phase space volumes in a chemical system as time progresses? So this is the march of equilibrium to higher, this is the march of entropy to ever larger values. And this essentially is the driving force behind the second law of thermodynamics. So second law of thermodynamics, you'll see in the other notes and videos I've posted, says that entropy of the universe gradually increases. But why? Why? So we're going to try and see why it increases now. So consider a gas cylinder being filled with a mass of molecules m, and you have 10 to the 22 molecules. So it's not quite a mole, but it's order of magnitude a mole. Why did I not just write 10 to the 23? Who knows? But 10 to the 22 is order of magnitude a mole, a little bit less. And let's say the volume of the cylinder C is 10 times the volume of the cylinder R. And these two cylinders are separated by a tap T. So let's say initially C is empty and R is full of gas. And then finally we open the tap and C is allowed to be filled. Okay. So the gas is going to flow from right to left. So the change in the Boltzmann entropy during the filling of C with the gas is going to be the delta SB, which is the final entropy minus the initial entropy, because entropy is a state function. It's a path-independent function. So we know that finally we have Boltzmann's constant. Here, K just means KB, or Boltzmann's constant. So it's going to be K log omega, remember, where omega is our ignorance. And remember we said it is proportional to the states to the number of molecules. So I've got one state, that's just the cylinder, but I've got m molecules. Okay. So here the 1 is just here 10 over 10. So maybe I should annotate that in case it's not clear to my students. So this 1 here is just 10 divided by 10, which is this volume here. Because that's finally where we're going to go, right? And I've got m molecules, okay, minus, because there's a minus, and then this 10 to the negative m, this is just 1 over 10 to the m, right? Which is 10 to the minus m, because, and it's this one here. So my initial volume, or the state, is 1/10 of the final volume. So hopefully that clarifies that. Maybe some students were looking at this wondering where that minus comes from. This is exactly where it comes from. So hopefully that's clear now. So then we have K. Remember that once the log applies to the parentheses, I can bring this m exponent down as a coefficient. So I bring the m down, so it's now km log 1. Likewise, I can bring the negative m down, but the negative m hits that negative and makes it positive. So I have positive m log 10, and then I can just get rid of this term because log 1 is 0. So this term disappears, and I'm left just with km log 10, which gives me a large number. So 2 by 10 to the 23 multiples of Boltzmann's constant, that's very large. So the point of this is, by increasing the volume size in the real world by a factor of 10, you actually scale the coarse-grained phase space by a factor of 10 to the 22. So it's not a linear scaling. So thus, although we allowed gas access to a volume that was 10-fold greater, the coarse-grained phase space volume, which is not a real phase, it's not a real space, it's an abstract mathematical phase space. And if I haven't mentioned phase space to you before, phase space is momentum location space where Newtonian mechanics happens. So you can imagine objects moving and colliding, and it's the Newtonian idea of objects moving and colliding that we use to think about a gas. Erroneously, but it's useful. Obviously, a gas is not Newtonian, but it's a useful way to think about it. So that 10-fold increase in real volume increased the phase space coarse-grained volume by a factor of roughly 10 to the 23. So visually, we can imagine we started here, and this is the increase. This is the march of the system to ever-increasing volumes of phase space. So imagine all of these. I'm saying volumes. Obviously, I've only drawn a 2-dimensional illustration here. But imagine this is 2D volumes that represent volumes of phase space, which is actually a 6-dimensional phase space. So I should probably mention here. Phase space is 6-dimensional, but it's represented here in 2 dimensions. So phase space is momentum P and location Q space. It's 6-dimensional because you have P, X, Py, Pz in the 3 Cartesian axes. And you also have location in the X, location in the Y, location in the Z. So that's where the 6 dimensions come from. Here we're just looking at 2 because 6 dimensions is impossible for the human brain to visualize. So we won't even delude ourselves that we could do that. But you can see this inevitable march through increasing volume size, and the maximum of all volume sizes is equilibrium. So over time, the trajectory of the item is coarse-grained in coarse-grained phase space, transitions to ever greater volumes until it enters the maximum volume. So if you imagine a rat was moving through these volumes. Rat was blindfolded, and every time it goes through a different volume, it goes through a door, and it's blindfolded. The likelihood of, once it gets into this big volume here, the likelihood of it ever finding that door again, and then that door again, and then that door again, are much less likely, not impossible, but much less likely than staying in that volume. So that's not only explains visually why entropy has a tendency to increase, and that's essentially what equilibrium is, the consequence of entropy tending to increase, but it has a tendency not to decrease because it's extremely more likely that it will increase instead. So if we have entropy S from the Gibbs perspective and entropy S from Boltzmann's perspective, we can consider that the Gibbs perspective is great looking at a microstate perspective, but from macrostate perspective, which is going to be more useful to us in general chemistry, we want to consider the Boltzmann idea of entropy, which is more applicable to the macrostate. So microstate means looking at each individual molecule. Macrostate means looking at the holistic collection of molecules, which is typically what we do in chemistry. So for example, just to convince you that the Boltzmann way is the way to go for us, if we look at coarse graining of phase space, imagine you had this array, and here we have one grid of the array occupied. And over time, this array, this black blob could be a blob of ink. Let's say we have ink, but over time the ink can spill. Let's say it's pointed up towards out of the plane of the page. A cup of ink, but the ink can spill. So over time, the ink is spilled and it spreads out and it infects or invades neighboring grids. The volume of ink won't change, so the volume of phase space is conserved. But remember, I've infected different boxes. Now, if each box is a volume of phase space, remember that volumes of phase space have massively different orders of magnitude 10 to the 22, massively different volumes. So here I've drawn them all the same size, but that's just because it's easier to do that. So imagine I've gone into this box now, but that box could have a radically different volume. So it looks like the volume is the same. So rather than remember to imagine, okay, the volume of phase space is massively different now, if you look at how we can show this with this probability density, imagine the same idea where the ink, our cup of ink now is spilt over time, but as it infected different cells with ink, we can say, okay, it's still mainly in this one, but I've got, you know, if I literally took that box, mixed in all this white shading with some of that black shading, it would give me this light gray shading. I've got a lot more black ink in this box, so it would give me slightly darker shading. This one would be lighter. I've got some black shading here, which makes this gray. So everywhere where the black has penetrated the box, I've got some extra shading. Now you can see that the volume has increased visually, rather than remember that each box of phase space is drastically different. So wherever the volume penetrated the cell, that cell adopted the non-zero density or shading. So we started off from an initial volume occupied here, and then finally we got to this much larger volume shown here. So clearly the volume increased. And remember, the volume is proportional to entropy. So we've shown visually using coarse graining, which literally means chopping the whole thing up into chunks, that we can naturally visualize this increase in our volume of phase space, which is our ignorance, which is our entropy. At this stage, please link this back to the decoherence that we said previously. So our ignorance that we've just seen increases with time is supposed to make you think back to this diagram here, where I know what you're doing, but as soon as you hit this stuff on the right, I start to have a much less likely understanding of what's going to happen on the right. And you can definitely know that going backwards in time, there's no way I can look at these things on the right and know what happened on the left. It's much less likely, or it's much harder to do than analyzing what happened going from left to right. So keep this decoherence image in mind as you reflect upon this visual here, this increasing volume of phase space. Okay, we're coming up. I don't think we have many more slides in this video. Let me just see where we are. In fact, this is the last page, and it's just to qualify something on the previous page, to be honest. So the reason, just to give you an idea of this phase space probability density here, think of each coarse graining as averaging. So imagine an empty pixel as white and a full pixel as black. Then and therefore a half pixel is a mixture of white and black. Well, microscopically, the above 3 pixels are all different. So I could distinguish white from white and black. But macroscopically, if I just average, the lower 2 are going to be similar. They're going to appear black, or at least they're going to be similar compared to the top sphere. So that blending is what I mean here by the shading, and that's why we include the shaded spheres, whereas we didn't really include the shaded spheres from the macroscopic perspective. Okay, and that concludes this video, which again accompanies these notes that I made available to my chemistry students.